say we can start the first session of our webinar series. Our first speaker is Dr. Wolfram Buss from the Australian National University and one of my former colleagues here from the University of Edinburgh. And he will be talking about biochar diversity and biochar-based fertilizers. So to see his screen, I think it should pop up on your screen as a full screen anyway. Otherwise, you have to click on it on the top bar on his picture. And just to make sure that no one gets disturbed by anyone else, please turn off your microphone during the presentation. That's on the bottom left side of your screen. So just click on your microphone and it will be turned off or on. After the presentation, we will have some time for questions. So in this case, either you write in the group chat or you just raise your voice by unmuting and then asking a question. We will try out what works best. So yeah, Wolfram, the screen is yours, I would say.
Thank you, Christian. I hope you can hear me well. If not, please write in, just write me a message or so that, or Christian, so we can change that. Otherwise, yeah, I'm giving the presentation from Australia, so it's already a bit dark here. I hope the lighting is good. So yeah, I want to talk about biochar diversity and biochar-based fertilizers, and most of that work I did still at the UK Biochar Research Centre, and was there for my PhD and postdoc, and then afterwards I came over to Australia, and yeah, I'm currently a visiting fellow at the Australian National University and at the University of Hohenheim in Germany. Yeah, so this is this presentation is based on the use of biochar in broad-scale agriculture mostly, but also sort of forestry, yeah, but generally for biochar's effect on plants and in soil. Okay, so yeah, why is biochar so great, and why are we actually so interested in it? And I think the main reason is that it has so many different benefits, it can tackle so many different problems with it. So you use a material that is typically a waste material, you upgrade that to a higher value product, and then you use that in environmental management. So you really tackle the sphere sort of waste management, environment, and in the case how I use biochar, then soil, so sort of agriculture, plant growth improvements. Yeah, so you clearly can see that there are sort of multiple benefits, and just quickly want to go through sort of how I see biochar and why I'm so interested in it, and that is because the different fractions of biochar can have really interesting effects on soil. So the mineral fraction can increase soil pH and supply nutrients. The carbon fraction can help to retain water, increase aggregate stability, and also cation exchange capacity. And the material together, sort of the minerals and the carbon matrix, can stimulate microbial growth. But I know probably a lot of other people are listening that are interested in other uses of biochar, and that is from soil remediation to absorption of nutrients and contaminants from wastewater. For example, using livestock farming or for energy storage. So there's really biochar is very versatile, and that makes it really interesting, but also really difficult really to understand and to use. And I think we'll hear in the second session about cascadic use of biochar. So that's again a really interesting area, since biochar can be, for example, loaded with nutrients and then used in soil, for example. So or different aspects, so you really can make a really good use of it. But as I said, it is an advantage that you can use it for so many different purposes, but it's also a disadvantage because you really need to know the material really well. And here I have different materials, so different feedstocks that we use for biochar production. And this is a photo I took while I was working at the UK Biochar Research Center, and it literally took me like 5 minutes just to make that photo, because we have so many different materials there. And as you can imagine, for example, if you use the material in the left top corner, which is a wheat straw, and make a biochar from it, it will have completely different properties to a biochar made from the material in the right bottom corner, for example, which is leftover from algae. Yeah, and the algae material will be very nutrient rich. The wheat straw, well, will have some nutrients, but will have a good structure for yeah, sort of nutrient absorption. And yeah, this obviously there's a real diversity in there, which is an advantage. But if you then want to use it for a specific purpose and you're not entirely sure what sort of biochar you have, if you're not entirely sure about the properties, you will basically get into trouble, because it might not really have the effect that you will want it to have. And if you then take the biochar production conditions into account as well, something like the highest treatment temperature, which increases the surface area a lot. It also increases the pH, while it, for example, decreases cation exchange capacity. This just makes the whole thing even more complex. And then you have other factors such as the residence time at the highest treatment temperature, a heating rate, or also the type of technology that makes the picture even more complex. And if you take those factors into account, the properties, or the range of values for different properties really gets immense. So if you compare, for example, there's just a list of sort of, I think, 4 or 5 references that I put together a couple of years ago, and it just really highlights that there is a huge range of so the magnitude of values is really enormous. For example, for surface area, you really, depending on the feedstock material and the production conditions, you can increase the surface area enormously. Similar with something like the nutrient concentration. It very much depends. Obviously, a woody biochar won't have basically no nutrients at all compared to a sewage sludge biochar or manure biochar, which has like a lot of nutrients. So you really need to know your material depending on the use. And that is often has resulted in not really great effects on plant growth, because people typically just took the biochar they had, applied it, and checked the results, and that also led to negative effects, partially or no effects at all. And specifically, I see that here in Australia, people are very disappointed by the material, and they have really stopped doing research. And I think that is really bad, because that just highlighted that there is more research need, and you need to really check for what purpose you want to use it for, and sort of check different soil properties, different conditions, and then really find out where it works best. And that sort of brings me to the challenges of the use of biochar in broad-scale agriculture. And the effect that I just highlighted was having reliable effects, because that's really the most important factor for economics. For a farmer, the farmer really needs to know what sort of effects he can expect if he applies it in the system. Because otherwise there's just no point of using it if the farmer isn't sure that it's going to have a specific effect, and that that basically there is an economic benefit. And then there's another sort of couple, so 2 things that are related, that is contaminants and risks, and related to that is legislation. So whether you're allowed to apply it or not, it always depends on really the country you're living in. It's quite different. But so my PhD was on contaminants and risks, and I think we know a lot about it, and we can pretty much produce biochars with really low concentrations of at least organic contaminants. And heavy metal is always tricky, because most of them stay in the material, and so you really need to have a material that is already low in contaminants, in heavy metals. And that is a problem because often waste materials are not. But the important thing is that really the availability is very low, the availability of those metals. And so most of the time they're not a risk. And I think that's the important part. But legislation hasn't really picked up on that. And well, that's very little we can do about that. But I don't want to talk about that really. I want to talk about the economic constraints a bit more, because there's a bit more to that story. So another problem is that biomass availability. So specifically in areas where you might need biochar, for example, in areas with degraded land. And here in Australia, we have a lot of this, dry areas where biochar would make a lot of sense, but you don't have enough. So biochar would make a lot of sense, but biomass is not available. And you would have to transport the biomass or biochar. And well, that's very expensive. And also the biochar production is really expensive. Since the demand for biochar is still really low, the production is really low, and the units are very expensive. And that means, yeah, it often doesn't make sense. It's just, if you see the unit on the right, this is a really tiny unit, and well, you can produce some biochar with it, but in an economic sense, yeah, it doesn't make much sense. In this case, it's used for truffle farming actually. And because it's such a high value product, it does make sense to produce biochar with it and use it. Because then even if you just increase the yield by a bit, the truffles are so expensive that you actually have an economic impact, but it is very rare. So economy of scale is really important there. And in China, this is currently happening, so that you can produce, or they're producing biochar much cheaper now because they have huge production units. And that's something we really need to achieve in other countries as well, to be able to make it economical. And also then the transport and spreading is very expensive. And the problem with there really is that if you want to improve soil properties, you need to apply something of around 30 to 40 tons per hectare of biochar or more. And for a farmer, that doesn't really make much sense. And it's similar if you want to increase like cation exchange capacity or do liming with biochar, as well as water availability. Increasing water availability, it all means you need to apply a lot of biochar. And compared to that, the fertilizer application rate is maybe 1% of that, maybe a bit more. And if you then do liming, maybe it comes up to, let's say, 1% of that, 2% of that. But still, that's not really much. I mean, compared to biochar application rate, that's nothing. So that's something we really sort of have to work on, and seeing that scale, I think, is important. So, and when I was thinking about that, I came up with sort of this idea, or not, it's not my idea, but the sort of a concept that it makes more sense to actually use biochar as a nutrient provider. So instead of applying a lot of biochar to improve soil properties, you apply biochar sort of annually and apply, let's say 3 to 5 tons per hectare, and then supply nutrients with that. And the advantages would be that you have a sustainable nutrients, basically. You do nutrient recycling because you use waste biomass. And it's important for food security as well, because you basically in parts, so you save some fertilizer, that most of the fertilizer, or a lot of the at least phosphorus fertilizer, is imported. So that would be important, and it is a direct financial incentive in the sense that you actually can replace some of the fertilizer that you're usually applying, so you know how much you're spending on that. And then you have much more predictable effects, because you know what you're actually replacing it with. So you're replacing normal nutrients with nutrients in biochar, and that is sort of, you can calculate the effects and the costs of it. And then you have the side effects that around 50% of the material is actually carbon. And that means you would still improve soil properties, also not straight away, because as I said before, the amounts you need are much higher than that. But over time, you will increase the or improve the effects, and also you do carbon sequestration as well. But there are some sort of challenges with that. Well, actually, the next slide is on challenges. Just quickly about sort of the nutrients in biochar. Since I'm not sure about the audience, I thought I'd just put this in. So nitrogen, you can sort of get nitrogen fertilizer out of the air, so that's not limited. You need energy, and if you have renewable energy, and then you basically can really produce a lot of nitrogen fertilizer. So that's not a problem. And in biochar, the nitrogen is mostly lost, so you do have to spike it afterwards with a nitrogen fertilizer. And for phosphorus, since phosphorus is a limited resource, luckily the phosphorus remains in biochar after pyrolysis. The problem there is really that the availability is sort of unpredictable and often low. So we need to have mechanisms. We need to know the mechanisms of phosphorus availability, and then also increase the phosphorus availability in biochar. Potassium is also a limited resource, but it's a bit more widely available than phosphorus, sort of that the resources last for longer, but also location-wise, it's not just limited to a few areas, but you can find phosphorus fertilizers in quite like more areas. And potassium also remains in biochar, and it mostly has a very high availability, and we actually even want to reduce the availability in some cases. And now just quickly about sort of the challenges. Biochar is a very different material compared to other organic matter, like compost actually, or also mineral fertilizers. And that's because of its high porosity, high pH, and also because pyrolysis converts organically bound nutrients into inorganic bound nutrients. And that means it's actually, you really have to start sort of from the beginning. While you have a long history of research into inorganic fertilizers, this is actually something quite new, quite different. And I think specifically the high pH of biochar makes it sort of quite a unique material in the sense of nutrient release. So if you want to produce a controlled release fertilizer, there are a few things we have to consider. And I'm just showing some slides now of my research. So far it was really mostly a long introduction, I guess. But now I'm just going to show a bit about the research that I've been doing. So first, a bit about sewage sludge biochar, which is rich in phosphorus and also other nutrients, but it's lacking potassium. So here as a comparison, phosphorus has around 2%, sewage sludge has around 2% phosphorus in this specific case, but it can have up to 10%. And the potassium content in this unenriched biochar that I was investigating was around 0.3%. And I was enriching that sewage sludge biochar with 2% and 5% potassium in the form of potassium acetate, and then I was pyrolyzing. Also, I was spiking the sewage sludge, and then I was pyrolyzing it at 700 degrees Celsius. And this figure just shows the potassium availability of the total potassium content, and then in different water extraction steps. So initially, the first step, it was around 40% of the potassium available, and then over time, I was able to get out all of the potassium, and that is actually something quite useful, because it means not all the potassium is straight sort of plant available, but also it doesn't leach straight away, but it will be available over sort of probably a vegetation period. So I still have to confirm that in plant tests, but I think that looks quite promising. So controlled K release, and then eventually most of the K is available. Here, this is another sort of experiment where I used a different potassium source, and that is ash, so pine ash, that you can apply onto soil straight away, but there's a bit of a problem with the very high pH, leaching of potassium, and also salinity, because it has a very high salinity. As mixed this wood ash with pine, so with its sort of source material, so to say, to have basically a better balance of nutrients and organic matter, and so to enhance the usually a very low nutrient content biochar with nutrients. So I mixed, just to explain it again, I put 5, 10, 20, and 50% wood ash in mixed it with wood, and then pyrolyzed the material. So, and the results from that are basically specifically for potassium availability. that in pure wood ash, around 60% of the total potassium in the material was directly extractable in the first extraction step, while if I had actually 50, 20, 10, and 5% of ash in that biochar, there was only around 20% of the K was available straight away. And that is in relative basis, so relative to the total potassium content. And that is, again, really promising, because that means the potassium content, potassium release is buffered, is moderated, and it wouldn't leach through the soil profile straight away. It would very likely be plant available, and then parts of it plant available straight away, and then more over time. What it also did was that it buffered the salinity, so the electric conductivity of the material was much lower, and the chromium availability was up to 160 times less, which is also, again, really promising, because it's a problem when you apply pure wood ash on soil. So you have a buffered nutrient release, and at the same time you would have soil improvement effects, because you have still a carbon-based material. And there was another sort of side effect, and that was that the stable carbon yield was increased. So that means up to 45% less feedstock was needed to produce the same amount of stable carbon. And that means, just generally, you have a more efficient pyrolysis process. And that is really good, because it means you lose less of the CO2 into the air, and you capture more. And that's how I came up with this sort of concept, which is combining biomass energy. Just start from the beginning. So if you capture CO2 with trees, and then you use the wood to use for bioenergy carbon capture and storage, you always have a waste material, and that is the wood ash. If you use the wood ash, you use some more wood, and then you produce those pellets that I showed. You pyrolyze those. You have a very efficient pyrolysis process, so you capture a lot of the carbon. You use that carbon, so that a biochar that is enriched with wood ash, put it back onto the soil. You basically supply nutrients, and you also improve soil properties. And then you would also have an increase in plant growth. You would use that material again for bioenergy carbon capture and storage in the next period. Basically, it's like probably a 30 to 40 year cycle. And that means you have basically more available, and parts of this, again, you would be able to use and put back onto the soil, having a sort of nutrient release that is buffered, but also carbon that you store in soil. Yeah, and then a little bit about phosphorus. Phosphorus is quite different to potassium, because its availability is very strongly pH dependent. And since biochar has a very high pH, this is becoming a limiting factor, and really very important for phosphorus release from biochar. So I was then thinking, what actually happens when you have a high pH biochar, low pH soil? Where does the P flow? How does it flow? Yeah, and the first thing how to really investigate that was to check how biochar changes the soil pH on sort of micro scale. And that is something that a former PhD student that started with me, Jessica Shepard, she started this sort of research. So had a look at putting biochar particles into soil, and then seeing how the pH changes over time. And then in this case, we had a look basically how much it changed with different biochars. And that was sort of the first step. And then we built up on that. We used different extractants at different pHs, and then basically extracted our biochar and analyzed the phosphorus. And that gave us sort of an indication at which pH range phosphorus was available and phosphorus was leaching out of the biochar. And I'm not going to talk too much about that, because it would get a bit too difficult, too sort of complex. Instead, I want to mostly show the last panel, because the last panel shows the limiting step. So under which conditions the phosphorus didn't leach out of the biochar, so it was basically not available at all. And that was when we had a pH range of around 7.5 to 9 and calcium present. And then we had precipitation of calcium phosphates, which is very well known in soil, that this is really a limiting factor of phosphorus availability. And here we were just able to show that it was the same sort of process in biochar. And in this case, the calcium came from the soil solution or from our extractants, which was done with calcium. But then I did some more analysis of previously published data, and I was also able to show that the calcium in biochar actually limits the phosphorus release. So in this case, the x-axis is the total calcium concentration in biochar, and the y-axis is sort of the phosphorus availability. And it clearly shows that the more calcium you have in your biochar, the less phosphorus is available. And that's a very important sort of relationship, because on that I then sort of based one sort of modification of biochar, and this is the last slide here now. So I modified the biochar so that the phosphorus was more available. It's again sewage sludge biochar with very low phosphorus availability. So you can see from again the water extractable P content in just sewage sludge is around 1%. In biochar is basically nearly below the limit of detection, very, very low. But then when I added so low cost additives, before pyrolysis, I was able to increase that to around 4% and then to around 8-9%. And that was an increase of just water extractable P content by around 200 times. And we're currently analyzing sort of the mechanisms behind that, and then hopefully publish that as well, because I think this is very promising to then produce a biochar fertilizer, because now we have a cost-effective method to increase the availability of nutrients, specifically phosphorus, which is really the most important one, and then are able to target, sort of produce a targeted biochar fertilizer that has a, in this case, for example, a high phosphorus availability, let's say a moderated potassium availability, but we would also be able to have a low phosphorus availability, which might be needed in sort of soils where you want to have a controlled, really slow release phosphorus fertilizer, like in pastures or so, where you really want to have applied once and then have it available over several years or so, which is not as intensive. So as a conclusion, I think biochar diversity is really important. It's definitely a strength, but it's also a weakness, and it has caused lots of issues and still is. And the biochar nutrient release can be controlled with different factors that we're sort of starting to understand. The benefits of biochar mineral fertilizers are that you have a direct monetary incentive, because you replace, maybe not completely replace, but you supply it in addition to mineral fertilizer, so you know what you're sort of replacing it with, so which part, and that means you can calculate how much it can cost. It might still be too expensive, but at least you have sort of a guideline, while if you just apply it for improvement of soil properties, it's a bit difficult to really would need a specific yield increase, which is really difficult to predict, regardless, even with under normal sort of standardized conditions without even biochar in it. And then you can produce a slow release, possibly precision fertilizer, by modifying the release of nutrients. And then still you have those extra benefits of waste management, of soil improvements over time, and also carbon sequestration. And that's why I think this is a really important concept. So yeah, I want to thank Christian for organizing this. I think this is definitely a great idea. Specifically also now I'm able to participate actually from Australia, and I don't have to be present to give this talk. So yeah, thank you very much for that. And otherwise, thank you all for your attention. Okay, Christian, it's you.
Thank you very much, Wolfram. Nice presentation. There were some questions. I don't know if you read the chat.
Yeah, no, I tried to ignore them because yeah.
It's a little bit strange to read them while you're presenting. I mean, one question was about the potassium is actually catalyzing the process, and you should get a lower yield. But I think you can say more about that.
Well, yeah, it's okay. I didn't read the whole question, but the thing is, that's absolutely true. What happened? It does catalyze the pyrolysis process, but it catalyzes the char formation. So that means specifically, I believe the secondary char formation. So you have the vapors actually coming back and really reacting with the carbon, and you produce more char. You don't produce less char. But I can also, I actually couldn't read the question now. Can't go. Yeah, so you produce more char because you do catalyze the formation of pyrolysis solids.
And I'm pretty sure, I mean, I know you published it, so you probably can just share the publication name. Was it our paper that you put it in? Synergy in BCCS, I think.
Yeah, I mean, there's lots and lots of references about using alkaline metals to catalyze char formation, so you actually get a higher yield.
Yeah. Okay, so if anyone has a question that you want, or he or she wants to ask Wolfram, so now is the time. So I think we wait 1 or 2 minutes in case someone writes something, and otherwise I will be the next one. So there's one. If you are able to answer that question, I'm not sure.
Which one? Sorry, I'm just
the last one now. What are the costs of your slow release fertilizer?
Well, that honestly, that really depends on the region, on sort of what material you have available. If you use, for example, the sewage sludge for it, you might even get paid to actually use that material for biochar production, because you use the waste material that's really otherwise has to be disposed of, and you have to pay for it. So if that actually would be the case, which is a problem because you might have a bit higher heavy metals, but that might make it really cost effective. If you then use something like wood ash, as I've shown, as a potassium addition to the sewage sludge, you might be able to produce the material really, well, hopefully really cheap. And I saw another question about that basically we sort of, how was it phrased, over design it or whatever. And I think if we just get the science right and then use waste materials for it and then have economy of scale, we can really produce those sort of highly designed biochar quite cheaply. We just need to get the science right, and that's why we do need to put a lot of research into that. But otherwise, I think we can produce it very cheaply.
Okay, thanks.